In this video, we're going to extend the rules of trigonometry to apply to angles greater than 90 degrees. At first, this might seem strange because we've been working with trigonometry within right-angle triangles, and you can't have an angle greater than 90 degrees within a right-angle triangle. It's a lot like when you first took the rules of addition and subtraction and extended them and came up with the negative numbers, or took the rules of exponents and extended them and came up with exponents that could be 0, negative, or rational. In the same way, this might seem a little counterintuitive at first, but we'll see that we can apply very similar rules to what we've been doing so far and come up with a whole new area of trigonometry. So first, let's recall that, for example, cosine of 30 is equal to the square root of 3 over 2. That means that the inverse cosine of root 3 over 2 is equal to 30. The same angle and ratio are paired. However, I've put a little ... here because it turns out that there's actually more than one angle that is associated with a cosine ratio of root 3 over 2. As we see down here, while cosine of 30 is equal to root 3 over 2, it's also true that cosine of 330 is equal to root 3 over 2. Now clearly 330 can't fit within a right angle triangle, so something else is going on here. And relatedly, cosine of 150 and cosine of 210 are both equal to negative root 3 over 2. So there's a relationship going on here that we'll see as we go on. So let's explore how this can happen, how we can deal with trigonometry when we're talking about angles greater than 90 degrees. And we're going to start from our familiar right angle triangle. So this is our right angle here, and if we define this angle as theta, this becomes the opposite side. This is the adjacent, and this is the hypotenuse. The first thing we're going to do is we're going to take that angle, and we're going to superimpose it on a Cartesian plane. We're going to put this angle theta here at the origin. So this is the opposite side, adjacent, hypotenuse. And now that we're on a Cartesian plane, we can use coordinates, and we're going to label this other side of the hypotenuse, not the one at the origin, but the other one, as the point xy. We're going to do that because we're going to start moving this around, and that'll help us keep track. Now, once we've labeled this corner as the point xy, we can relabel the sides instead of opposite, adjacent, and hypotenuse in terms of these numbers. So if this point has coordinates xy, this distance here, which is the same as the distance up here, is x. And this distance here is y. So this side becomes x and this side becomes y instead of adjacent and hypotenuse. And using the Pythagorean theorem, we could work out this side in terms of x and y. So if we call this side r, then r squared has to be equal to x squared plus y squared, or r is equal to the positive square root of x squared plus y squared. So now instead of labeling the triangle adjacent, opposite, and hypotenuse, we've labeled it x, y, and r. That allows us to come up with new definitions for the sine, cosine, and tangent ratios. Instead of sine theta being opposite over hypotenuse, now we've relabeled opposite as y and hypotenuse as r, so sine theta is equal to y over r. Instead of cosine theta being adjacent over hypotenuse, we can call it x over r. And instead of tan theta being opposite over adjacent, we can redefine it as y over x. So the new definitions are sine theta is equal to y over r, cosine theta is equal to x over r, and tan theta is equal to y over x. And the advantage of this system is that instead of the old opposite, adjacent, hypotenuse system, this one is going to be applicable anywhere on the Cartesian plane. In other words, we're going to be able to move that point around and essentially dispense with the triangles by defining the ratios in terms of x, y, and r. So let's look further at how that happens. To do that, we're going to introduce a bit of terminology. Here's our right angle triangle again with the right angle here, and we call this the angle theta. We're going to call this arm here of the angle the initial arm. It's the arm we start from, and it's going to rest on the positive x-axis and stay there. The other arm here, we're going to call the terminal arm. So the angle theta is between the initial arm and the terminal arm. We call the angle theta the principal angle. It's the angle we're going to be principally or primarily concerned with as we go through here. And we also describe the angle theta in the counterclockwise direction. So angles going counterclockwise we're going to call positive, and as we'll see later we can have negative angles as well. So this is the initial arm on the positive x-axis, this is the terminal arm, and the principal angle, theta, is the angle between them going counterclockwise. We're also going to introduce another angle, the related acute angle. The related acute angle is simply the angle from the terminal arm to the closest x-axis. In this case, the closest x-axis is the positive x-axis, so the principal angle theta and the related acute angle are the same. We often use alpha, sometimes you'll see textbooks use beta for the related acute angle. So again, principal angle is the angle between the initial and the terminal arm. Related acute angle is just the angle from the terminal arm to the closest x-axis, and that'll become clearer as we go through a few more examples when these two start to differ from each other. We describe an angle as being in standard position if its initial arm is on the positive x-axis, so all the angles we're going to deal with are in standard position. Now, let's actually give this angle a value. Let's say that this is 30 degrees. So if theta is equal to 30 degrees, then this is one of our special triangles, and we know that the sides are in the ratio 1, 2, and this bottom one is going to be root 3. We're saying that's 30 degrees. Now again, if we've labeled this point with its coordinates on the Cartesian plane, in this specific example, its coordinates are going to be root 3, comma 1, because we have to go root 3 over and 1 up. Now, if we use our new definitions for sine, cosine, and tangent, sine of 30 degrees is going to be equal to y over r. The y value is 1, the r value is 2, so we get 1 over 2. Notice that this is the same as we got before when we were using opposite over hypotenuse. Cosine of 30 degrees is going to be x over r. X in this case is root 3 because x means the x-coordinate of this point at the end of the hypotenuse, so we get root 3 over r, which is 2. And tan 30 is going to be equal to y over x. The y value is 1, the x value is 3, so we get 1 over root 3. So far, the answers we've got have all been the same as we got before we introduced this new concept, but that's going to start changing in a moment. So in this picture, what we've done is we've taken the triangle from the last picture and we've reflected it across the y-axis. So if we go back to here, we're taking this triangle and reflecting it across the y-axis. All the measurements are going to be the same, so this angle here is still going to be 30 degrees. This length is still going to be 1, this one root 3, and this one 2. Now that means that this point is going to be the point negative root 3, because we've had to move root 3 over this way, comma, 1. Different from here where it was root 3, 1. Again, we've reflected it across the y-axis, making the x values negative. If this is 30 degrees, then this angle here is 150 degrees, because to get to the terminal arm, we'd have to go from here, the positive x-axis, around to 180, but then back 30, so we get 150. Again, the initial arm is here. It stays on the positive x-axis. The terminal arm is here. So the principal angle theta is the angle between them, and it's 150 degrees. But this angle here, the 30 degrees, inside our little right angle triangle, this is our related acute angle. We're calling it alpha, and in this case it's 30 degrees. So now the related acute angle is 30 degrees, the principal angle is 150 degrees. Sine, cosine, and tangent we're going to apply to our principal angle. So sine of 150 degrees, which is going to be y over r, we take our y value, which is 1, and divide by our r, which is 2. Now things start to differ from what we've seen before though, because cosine of 150 is going to be defined as x over r, and now the x value is negative. So negative root 3 over 2. So cosine of 150 is negative root 3 over 2. And tan of 150, which is y over x, is going to be 1 over negative root 3, which we would just write as negative 1 over root 3. Let's continue the process. Now if we reflect that triangle downwards, again, this is still going to have length 1, 2, root 3, and this angle is still 30 degrees. That means in this case, now we're going left and down, so this point has the coordinates negative root 3, negative 1. And if this is 30 degrees, if our related acute angle is 30 degrees, our principal angle from the initial arm to the terminal arm going counterclockwise is going to be 180 degrees to get to here, and then 30 degrees to get the remaining distance, so that's going to be 210 degrees. Sine of our principal angle is now sine of 210, which is going to be y over r, and repeating the same process, now the y value is negative, so we get negative 1 over 2. Cosine of 210 is x over r, it's negative, and tan of 210 is going to be y over x. Now in this case, notice that both y and x are negative, so the negatives are going to cancel out. We get negative 1 over negative root 3, which is just 1 over root 3. Notice that x and y can be positive or negative because they are coordinates, but r is a length, so it's always going to be positive. Let's continue. Now if we reflect again across the y-axis to get into quadrant number 4, again, the related acute angle is the angle between the terminal arm, which is here, to the nearest x-axis. It's going to be 30 degrees. This side length is 1, this one's root 3, this one's 2. The x value is positive, but the y value is negative. If we go all the way around back to where we started from, that's 360 degrees, but then we'd have to come back 30 degrees, so that means this angle here, the principal angle theta, is 330 degrees. Sine of 330 degrees being y over r is going to be negative 1 over positive 2. Cosine of 330 degrees, x over r, both of those are positive in this case, so we get root 3 over 2. And tan of 330 degrees, which is y over x, y and x here differ in sign, so we're going to get negative 1 over root 3. So what we see then is that there's a family of principal angles that all share the same related acute angle. For example, principal angles of 30, 150, 210, or 330 degrees all share 30 degrees as their related acute angle. And we've also seen that the sine, cosine, and tangent ratios of all the principal angles in a family, that is, all the principal angles that share a related acute angle, have the same absolute value, but they differ in sign, positive or negative, depending on the quadrant. So, if we just look at the cosine ratio, for example, cosine of 30 degrees was root 3 over 2, but cosine of 150 degrees was negative root 3 over 2. Same absolute value, both versions of root 3 over 2, but this one's negative. Cosine of 210 was also negative, root 3 over 2, and cosine of 330 was positive again, positive root 3 over 2. So we can think about the signs of these, positive or negative, based on whether x or y are positive or negative. And this gives rise to what's commonly referred to as the cast rule. So let's remember that sine of theta is defined as y over r, cosine of theta is x over r, tan of theta is y over x. And consider that r is always positive because it's a length. But x and y are coordinates, so they can be positive or negative. Now because sine theta is equal to y over r, and r is always positive, sine theta is going to be positive whenever y is positive. In other words, in the top half of the Cartesian plane. So sine is going to be positive over here and over here. And I'm going to write S for sine where it's positive. Now cosine theta is going to be positive when x is positive because r is always positive. So the sine of this is going to depend on the sine of x. So cosine is positive in the right half of the Cartesian plane, there and there. And tangent is going to be positive when the signs of x and y are the same. If they're both positive, tan theta is going to be positive, but if they're both negative, tan theta is also going to be positive because the negatives will cancel out. So x and y are both positive up here, and they're both negative down here. Therefore, tan is going to be positive. Now, if we relabel this, where all of the different ratios are positive, with an A, then we get, again, what's commonly referred to as the cast rule, C-A-S-T, the letters spelling out which of the primary trigonometric ratios are positive in each of the 4 quadrants. All of them are positive in the first quadrant, only sine is positive in the second quadrant, only tan is positive in the third quadrant, and only cosine is positive in the fourth quadrant. And you can look back at the examples that we worked through with 30 degrees as the related acute angle to see that that's illustrated in that example. Let's look at some practice problems. Find the exact value of tan 240 degrees. We start by drawing a diagram. Then to get to 240 degrees going counterclockwise from the positive x-axis, we'd have to start here, go 180 degrees to the negative x-axis, and then an additional 60 degrees. That means that our related acute angle, the angle from our terminal arm to the nearest x-axis, is 60 degrees. So we know that tan of 240 is going to be related to tan of 60 somehow. Just as we saw in the previous example we worked through, all of the principal angles that have the same related acute angle, so all of the principal angles that have a related acute angle of 60 degrees are going to have the same sine, cos, and tan ratios, just differing by whether or not each of those is positive or negative. That means that if we can find tan of 60 degrees, we're well on our way to finding tan of 240 degrees, because the two will only differ by whether they're positive or negative, perhaps. So we know that tan of 60 degrees from our special triangles is equal to root 3. Now we use the cast rule to figure out whether in this quadrant tan is going to be positive or negative. And we see that tan is positive in this quadrant. So tan of 240 degrees is going to be exactly the same as tan of 60 degrees. They both have the same related acute angle, and they're both going to be positive. Tan is positive up here for 60 degrees and positive down here for a principal angle of 240 degrees. So tan of 240 is exactly equal to tan of 60, which is equal to root 3. So the process that we took was we drew a picture, figured out the related acute angle for 240 degrees, worked out the tangent of the related acute angle, which is root 3, and then worked out, using the cast rule, how tangent of 240 is related to the tangent of the related acute angle. Let's do another example. What if we're asked to find the tangent of 120 degrees? So in this case, if we draw our picture, 120 degrees, we go 180 degrees to the negative x-axis, so 180 degrees around here, and then back 60 degrees. So again, our related acute angle is 60 degrees, but this time, if this is 120 degrees, we're in the second quadrant, just like here, the principal angle of 240 put us in the third quadrant. Okay, so we know that tan of 120 is going to have the same absolute value as tan of 60, because they share the same related acute angle. So tan of 60 we said was equal to the square root of 3. However, by the cast rule, we see that only sine is positive in the second quadrant, so tan is going to be negative. So tan of 220 is going to be equal to negative tan of 60 degrees. Tan of 60 degrees is positive, tan of 120 has to be negative, so that's equal to negative root 3. Again, the process, draw a picture, figure out the related acute angle, and then work out the sine using the cast rule. Let's do another example. Here we're being asked to solve the equation theta is equal to the inverse sine of negative 1 over root 2, where theta is an angle between 0 and 360 degrees. So this negative makes the question a little bit more difficult. So let's solve something slightly simpler. Let's evaluate this, the inverse sine of positive 1 over root 2. What this is asking is what angle has a sine ratio of 1 over root 2. And we know from our special triangles that 45 degrees is one such angle. Now, what we've just done is find our related acute angle, because by making the sine ratio positive, we've essentially moved it into the first quadrant. All ratios, sine, cos, and tan, are all positive in the first quadrant. So this is now our related acute angle of the final angle we want to find. In other words, we've just found alpha. So the second step now is to draw a picture and use the cast rule to consider which quadrants sine is negative in. And sine is negative in the bottom half of the Cartesian plane in quadrants 3 and 4. So we're going to place our related acute angle of 45 degrees, which we just found, in quadrants 3 and quadrants 4. Now, to get from our initial arm to our terminal arm going counterclockwise this way, we'd have to go 180 degrees plus another 45 degrees. So one answer for theta is 180 plus 45, or 225 degrees. And the other one is going all the way around to 360, but then having to come back 45, and that's going to give us 315 degrees. So to review, what we did then was we changed our ratio if it was negative to positive. Sometimes you'll be given a positive ratio, and that step will be done for you. And then we took the sine inverse. That gave us our related acute angle. We drew a picture, placed the related acute angle in the appropriate quadrants, figuring out which ones those were by the cast rule, and then we worked out our principal angle from our drawing. The last thing we need to consider are coterminal and negative angles. Coterminal angles means exactly what it sounds like, things that share the same terminal arm. In other words, they differ by multiples of 360 degrees. In other words, an angle of 30 degrees, like that, has an initial arm on the positive x-axis and this terminal arm here 30 degrees away, but so does 390. If I imagine taking that initial arm and swinging around all the way around, it's going to be superimposed on this one. So 30 degrees and 390 are coterminal. Negative angles are those which involve a clockwise rotation. So if I were to start from here and rotate my terminal arm, say 45 degrees this way, that's a negative angle. So I count that as negative 45. To illustrate, let's find a positive and negative angle coterminal with 100 degrees. So positive 100 degrees means 100 degrees going counterclockwise, like that. So to get there going all the way around would be 360 plus another 100 degrees. So 360 plus 100 degrees is our first coterminal angle, and that's 460 degrees in the positive or the counterclockwise direction. However, we could also get there by going 100 degrees less than 360 in the opposite direction. So negative 360 plus 100, or negative 260 degrees. So positive 460 and negative 260 are both coterminal with 100 degrees. And that's the end of this lesson on trigonometry with angles greater than 90 degrees and outside of the first quadrant.